Hi, my name is Tree, and I'm currently a student at Oregon State University pursuing a Bachelor's of Science in Computer Science. Today, I'll be presenting the research I've done during my internship with AgAid, where I spent my time designing a digital twin of an agricultural experiment station leveraging LLMs and modern web technologies. I worked on this project in a hybrid setting where I spent the first 2 weeks in Merced, California, working at UC Merced's Parallel and Distributed Systems Lab. For the rest of my time, I worked in a remote setting. This project was done under the supervision of Dr. Zhao Yi Lu and my project lead, Adam Weinbrim, who was a PhD student under Dr. Zhao Yi. So, before I dive into the motivation for this project, I first have to talk about what a digital twin is. So, a digital twin is a virtual replica of some physical system or processes that use data to mimic its real world counterpart. So, this twin can virtually simulate the behaviors of that counterpart, and the benefits of doing that allow for a better monitoring and analysis of that system. And this will lead to improved decision making for the real world counterpart. So, because of this, these benefits can also be cost effective because its insights from that may lead to more efficient operations. UC Merced also has its own agricultural experiment station called the Experimental Smart Farm, which is a farm that they use to research and develop new technology and solutions that address agriculture issues, things like soil health, sustainability, and crop yields. Because this smart farm helps develop new technologies through research, this could lead to improvements in productivity while reducing costs, which not only helps the farmers but also the community that surrounds them too. And the motivation for this project comes from combining these two things. What if we created a digital twin of the experimental smart farm? This would be beneficial for one because if we could use that digital replica with the experimental smart farm, we can monitor its systems and then in turn use it to make future predictions using its own data. So the goal for my research was to design and develop a digital twin of the experimental smart farm by leveraging a large language model or AI tool and use modern web technologies while doing it. So I was tasked with building a working prototype of a digital twin that simulates the core features using dummy data, and this application is to be integrated with an AI model that will dynamically update the interface using natural language so that it can be easily used by its users, such as farmers or agronomists. I also wanted this research to be the foundation of future data integration and lay the groundwork for a more scalable digital twin in the future. My role in this project was the lead developer, where I oversaw the entire software development process. So during my first week, I was given this wireframe by Adam as the design reference for the digital twin. As you can see on the left side, the wireframe contains a natural language interface to interact with the AI assistant to update and modify the rest of the application using natural language. At the top, we can see there are data model choices that represent the predictive analysis of certain variables. Below that, we can see the plot of interest, which is a selected data model choice to be displayed. Below that, we have the census systems, which has our sensors, the status, and the overview of the sensors represented in a line graph. To the left of that, we have our interactive 3D representation, which is a 3D representation of the experimental smart farm with key marked points of interest as well as controls on the screen. Below that, we have our alternate aggregate forecasts that have symbols and signals, as well as a percentage. Below that, we have a temporal timeline interface, which also has marked key points. And we also have a date selector. I was also given the task of choosing the tech stack that I will be using for this application. So for my front end, which is the interface that the user will be seeing and interacting with, I chose TypeScript as my programming language and React as my framework. For the backend, which is the behind the scenes portion that manages all the data, I chose Rust as my programming language and Axiom as my framework. The LLM or AI assistant that I use to integrate into the application is a Gamma 327B model that is hosted in the cluster in UC Merced. For version control, I use Git and GitHub to help me track and manage changes made throughout the application. During my development process, I wanted the application on startup to call for information from the backend server and return that information to be displayed on the interface. So during the design process, I first had to develop the raw interface where I began designing the layout of the application, and after that, design each component that was displayed in the wireframe. Once I had done that and tested the front end, I then started working on initializing the backend or server that will hold all the information for the application. This backend will accept incoming requests from the front end and return the response back, which is the data that will be displayed on the front end. And this is important because by integrating this backend, we can have many different interfaces interacting with that same backend to receive and display the data on different devices. And from there, I worked on integrating the AI model to the backend so that once the front end interface sends a prompt and interacts with the backend server, the backend can then send out that prompt to the LLM. And from here, that AI model will stream a response back to the backend server, and then the backend will send chunks of data to our front end interface with the AI model's response, as well as data that will update the interface. So this is the current working version that I have right now of the digital twin. On top, we can see we have data model choices, and once you select them, they are displayed in the plot of interest. If we want to have it in a bigger view, we can click on it, and it'll open a modal to display it. Below that, we have our sensing systems with 3 columns: the sensor, the status, and the overview, where the sensor displays the name, the status displays the status of it, and the overview is a line graph of the sensor. Here we have our aggregate forecast. We can click and view these as well. And these also show the icons that were displayed in the wireframe. Below that, we have our temporal timeline, which we could drag and scroll through a selected date. We could also change the start and end dates of this as well. And you can see the icons also move as well because each icon above it is associated with a certain date. There we go. Now going back up, we have our 3D model here. We could click and drag and move the model to view it. We could also use the on-screen controls implemented to move up and down and zoom in and out for the model. So I have an icon that displays more information about the farm, as well as a squelch button to hide these hotspots that are displayed, or these points of interest. We can also click on each point of interest and it will display information about it as well. And from here, we'll move on to the natural language interface. And currently, the working version only is allowed to change dates. So I'm going to set the date to October 23rd, 2024. And if you look on the right side, you can see some of the data change while the AI works right now. Cool, we have the data changed. And now we could scroll and look through these choices as if we did before. The significance of this current version shows that dummy data can be sent from our server to the front-end interface, and the data given can be visualized as well. This current version also shows that we can implement an AI model to dynamically update the interface using only natural language. Future steps from here include integrating with a database that contains information from the experimental smart farm to help monitor long-term data and scalability. Another improvement that could be made upon its design is to implement an AI model that is more closely trained with the data from the experimental smart farm. Currently is running a more generic model. And from there, improvements on the front end can be made to ensure that the interface is comprehensive with the real-world data given. I would like to thank AgAid for the opportunity to conduct and present this research and being helpful throughout this entire journey. I would also like to thank Dr. Xiaoyi Liu for directing the project and Adam Weingrim for both his leadership in this project as well as his mentorship. I would also like to thank UC Merced and the Parallel and Distributed Systems Lab for the use of their facilities. And I'd like to thank you all for taking the time to listen to my presentation, and I am open to take any questions from the audience.